Hi everyone.
Um,
Okay.
just for a second. So we have Arya Mazumdar, who is going to talk about binary iterated hard thresholding. He's a professor in the Data Science Institute at UCSD, and he has other appointments in computer science and electrical engineering. Okay.
Thanks, Purna. Right, I just assumed that everyone knows me.
Can we go in like 15
No.
minutes?
Okay, so this is
After
a
this
joint
session,
work
because
with Nami Matsumoto, who is actually the star of this work, and she is right over here. So stop by to say hello to her. So Nami's work has been supported by the Encore Institute, and she recently also got the NSF Graduate Research Fellowship. So it's entirely supported by NSF. She's doing, this is the work that she did in her first year, and I am extremely proud of this work. So here is, so the talk that I'm going to give is going to relate to both the last talk that Hamid gave and the one before his that Puna gave. So there will be elements of both the talks present in this one. So maybe it's a natural collaboration that we can have with these two folks. Okay, and I'm going to talk about compressed sensing problem briefly to remind you of what it is, and also introduce the problem of one-bit compressed sensing. So you have an image. This is an image of Lake Tahoe, and although this looks high-dimensional, many from your signal processing backgrounds, you might know that this is actually a very low-dimensional vector hiding in a high-dimensional scenario. So you can actually compress it extremely. If you just do PCA or something, there will be only few components because it is so smooth. So, we acquire so much information from nature by sensors and by sensing, like your digital camera has all those things. And after that, you're going to throw away most of this anyway because you are compressing. So in compressed sensing, you sort of combine these two blocks and say via linear operation. So you say that, okay, I have some sparse vector, and it can, so without loss of generality, we can assume, if it is a known basis, we can assume the signal itself is sparse. It could have been sparse in the Fourier domain or so on. That means it has only k non-zero entries, whereas it is actually n-dimensional. And then what we do is to take samples from the image by multiplying with this matrix, which is m by n, and m is much less than n. And then we have this operation y equals to ax, right? And this can be actually implemented in hardware, which has been done in Rice University. It's like all these stories about compressed sensing. It was really very active area of research. I think it still is, but to a lesser extent. About for 10 years from 2005 to 2015. So our aim is to reconstruct this vector x from y, right? So we want to first design a matrix with small number of rows. That will mean that we are compressing it. And then we want to find an efficient recovery method that gives us back x from y and a. So that's the task of compressed sensing, right? So the one-bit compressed sensing problem is the following, where we further quantize it, because of course we are not going to store real numbers, so we are going to quantize it anyway. So why don't do an extreme quantization, that is, we are just keeping the signs of the vector, signs of the entries of the vector y, right? So we have samples of this format, and this is important because this is giving an extreme quantization scenario. So if you can recover from here, then maybe there are other like neural nets or autoencoders. From there, you will be able to recover. This is actually a, like a one hidden layer neural net. You can think of that. So it's like also a nonlinear operation. Simplest of the like one of the simplest of the single index model, where this link function or something called the generalized linear model, where the link function is just the sign operator. It is also learning a sparse half space, because you are basically getting to see with each of the samples from the measurement matrix, you are getting to see which side of this sparse vector this measurement lies. And then from there, we want to reconstruct this hyperplane that is separating everything. So that's learning half spaces. We are just learning sparse half spaces, right? So this is an interesting problem, and there have been a lot of work. So here is what we seek in a very clean way. So we are getting to see y equals to sine of ax. We know that x has only at most k non-zero entries. So we can slightly relax all of these conditions. I mean, X doesn't have to be exactly sparse. It can be approximately sparse, but I think even the sparse problem was quite non-trivial, but we can do all those type of extension. There can be noise in the system and so on. I'm going to briefly talk about that. Notice that we are not preserving the norm of AX anyway. When we are doing sign operation, like the dimensionality is actually being killed off. So we are not getting any information about the norm. So let's just assume that X is unit norm and we are basically recovering just the direction, right? So here is our aim. We want to minimize the number of measurements and we want to come up with an efficient recovery algorithm to give us some X hat such that the L2 error is less than epsilon. Right? So now the question is twofold. What is the minimum value of M? Right? And what is our efficient recovery algorithm to get this X hat? Okay. So so these are the baselines for this problem. First of all, there is a lower bound that shows us well, unlike what Pona did, I'm going to hide a lot of log factors here. So and our two parameters are k and epsilon. We are trying, so all the log n factors are sort of hidden over here. So sometime I will use tilde to explicitly mention that they are hidden. So I'm getting the sample complexity or the number of measurements has to be at least k over epsilon. Right? So that's something that is like an information theoretic lower bound. So you see, this is some sort of compression. So if you go through information theoretic lower bounds, so that will give you something like an epsilon net, which is k log 1 over epsilon. So so because it is a very specific type of compression where we are taking a linear operation followed by a thresholding, the lower bounds are different, right? So you need some geometric argument to make this work. It's also known that it is sufficient to have about k over epsilon log n over k epsilon, that many number of measurements, that is sufficient. And the sufficiency can be proved by choosing Gaussian measurements, and the recovery is maximum likelihood, or like an exhaustive search in the space of all possible signals to see which one maximizes the probability. So so the reason that this works is some rotational symmetry of Gaussian hyperplane. So if you basically pick a Gaussian hyperplane and if you have any two vectors, say x and x prime, the probability that they are in the, so you see the Gaussian hyperplane sort of uniform in all directions. So whatever is the angle that they are mapping, right? So the probability that they will be separate is actually proportional to the angle. I think there should be an inequality sign over here, sorry. So this is known. So we have upper and lower bounds. However, we do not have, so this is an exhaustive search or maximum likelihood. So we don't have anything efficient to give us this. Otherwise, we know the fundamental limits, barring this log term, which we are eventually going to hide. Right. So of course, now the problem is how to efficiently get to the optimum, right? And it's been there not from 1936 or 65. I think it's there since 2010 or so. So we know these baselines, and then it's an open problem how to efficiently get there, right? So of course, one of the first things that you do is to see, okay, I have all these measurements, so they are sort of giving me linear conditions, and I'm trying to find a feasible vector over there. So that's sort of a, but I also have, it's non-convex because I want to find the sparsest feasible vector, right? So what you do is you do some convex relaxations instead of this norm, like the sparsity, you look at the L1 norm, and there is this work by Plan and Varshnyin that gets you to get that gets the task done with k over epsilon to the power 5 number of measurements. So that many samples. There are other log terms, right? So it doesn't really get to that k over epsilon. The error term is actually pretty bad, right? So what is the other obvious thing for us to do is what actually like we would think of doing is to run something like a gradient descent, right? But it is a projected gradient descent, and this projection operation is sort of non-convex because we are looking, it's like we are looking for a sparse vector. So what we are going to do is to project it back to the top k coordinate. So we have some loss function. I'm going to show you the loss function. So and this is the gradient of the loss function. I'm going to zoom in on this gradient a little bit. So yeah, so and then this is the projection operation on the top k coordinates. So this has a name. This is called iterative. Like in compressed sensing as well, people do the same thing, and this is 1-bit compressed sensing. It was called iterative Hart thresholding in the context of compressed sensing. Now it is being called binary iterative Hart thresholding, right? And this algorithm was also there from around 2010 or so, right? So this is the projection operation. Okay, so let's look at the gradient over here, because I think it's nice. It has connection to some other problem. So what we are basically doing over here, and where is that term? Sorry. Yes. So that's our gradient. I don't know what this thing gradient of, but what we are doing is we're looking at the mismatches. So I'm doing an iterative estimation of x, right? So at the tth iteration, I have some x hat t minus 1. So I'm looking at the signs and seeing exactly where, in which measurements there are mismatches, and then what I'm doing is averaging out those mismatches, right? So the thing in the bracket that is giving me mismatches, right? And then I'm multiplying with A transpose. A is this matrix. That means I'm looking at those rows of A and taking an average of this. This is exactly like a batched perceptron type thing. Like if I had just one measurement, then I'm basically taking a step towards that, right? And now I have a bunch of measurements that are mismatched. So I'm averaging them out and then taking a step. So it's a very natural algorithm to learn half spaces, right? So that's my algorithm. And this is over this loss function. And I'm not, so basically this is minimizing the effect of mismatches and subject to sparsity and unit norm. So I'm actually taking this gradient step over here, and then I am projecting back according to the sparsity, the top k coordinate. So this algorithm were then tried to analyze and see whether this is giving us optimal sample complexity, and there is again a series of work. So it was known that just one iteration of VIHT will give you something like k over epsilon to the power 4. Right? And then this has been improved to k over epsilon square. And there it sort of stopped since 2017. And there is a reason why it stops over here. There is another work in 2019 that says beyond first iteration, iterates remain bounded, so the things do not get worse, but it doesn't show you the things get improved. So we don't have the optimal dependence on this error rate. So it's like k over, we want to still take it to k over epsilon. And this is actually a big deal because it shows up like in experiments, VIHT or the iterative Hart thresholding that performs really well, right? So we should match the optimal sample complexities, but cannot. Okay, so then there is another paper. Again, Plan is there, Friedlander, and so the usual people who work on these things, and they get something like this, which has sort of optimal dependence on error rates, but very suboptimal dependence on everything else. And there are constants like 24 to the power 48 involved there. So it's just like more bigger than the number of particles in the visible universe or something. So if your k and m all are bigger than that, even then you have to have like something like k to the power 3.5 or so, and then there is a k to the power 10. So there is like it's optimal dependence on error, but it's like a super suboptimal in a number of other things. But they sort of had some key ideas that we ended up using. So here is our result. We basically take it down to k over epsilon and log n over k square root of epsilon. So it's more or less optimal. And we basically, we also give the exact dynamics of this iterative Hart thresholding, like so this is basically, this is the distance projected to the unit sphere, so geodesic distance, and that goes down exactly in this manner. this is the portion of the sign distance that Una talked about. Second, we can show that there exist universal measurement matrices. So there is one matrix that works for all sparse vectors, and we can give exact characterization of those matrices. So those matrices, so it's not like we rely on Gaussian matrices, although we have not found any other matrix except for Gaussian matrices to satisfy the property. But if the matrix that we are measuring with satisfies some property, then we know that the dynamics will be like this. And then we show that, well, Gaussian matrices do have that property, right? One next step that we were able to make since then, and again, Nami has finished working on this, so that this BIHT is also stable. Like even if an adversary comes and flips a constant fraction of the results, y equals to sine x, so, but maybe only in 1 minus tau fraction of the measurements. In the other fractions, they sort of have arbitrary things. Even then, BIHT is going to perform well. It's not, the error is not going to blow up. As a matter of fact, you will still have the eventual error. This is again L2 norm bounded by something like epsilon plus tau. And so it's not changing a bunch of measurements. It's not going to completely destroy the thing. This is going to just translate into this much amount of error. Okay. How much time do I have? No time, 1 minute. Okay. So I will just keep a few things. So the thing is, so again, here is what we are showing. We are showing that there is some property called the restricted approximate invertibility condition that depends on k, n, and epsilon. And we show that Gaussian matrices with this many rows leads to that property. And then there is another part that if you have that restricted approximate invertibility condition, then you will have the BIHT recurrence that I have just shown. So here is exactly the restricted approximate invertibility condition, which is some sort of isometry that shows that there is some, that shows that if you just look at the distance between x and y, and if you look at the projection of those sign distance between x and y, there are certain relation that they maintain. Okay, so I'm just going quick. So what I want to say is that here is so just going back, the main challenge and why. So you see, so these are all, suppose these are all Gaussian measurements. Now how my algorithm is proceeding is that we get the mismatched measurements and then we average them out and we make such a state, right? When the points, when my estimate is far from the actual thing, the number of mismatch is large. Therefore, I have a large number, I'm averaging a large number of Gaussian vectors, and I have very strong concentration inequality, so I'm going to the right direction. But there is a point when I come close enough to the actual, my optimal point or whatever my answer was, and then there will not be that many mismatches. When there is not many mismatches, I'm actually averaging out a small number of Gaussian vectors, and I lose all those concentrations. And that's what happens. So if geometrically, if we try to see that if I am far away from, say, x, so there is this small circle, I can come up to that point, and then I cannot go close by this analysis, and that's why all the previous results had this k over epsilon square. But we can actually control something else at that stage. We can count the number of different sign vectors that are produced by a small ball. So you are so close that now you cannot really show that you are converging to the actual point, but there is not too many bad directions that you can go to anyway, right? So you will sort of gravitate towards the optimal. So you need a different type of analysis for that. Okay, so that's essentially it. There are quite a few open problems. For example, we are doing some sort of normalized BIHT where we are actually, there's the projection operator in unit norm that makes it super sensitive to step size. I mean, we have to choose some step size to make it successful. Whereas if you don't do that normalization, in practice, it converges fine. I mean, it's not as sensitive to step size. So is there, can we do something about it? And also we know only Gaussian matrices that satisfy RAIC. Is there something else? We dealt with adversarial noise, but then there are other kind of noise. And one of the things that we are looking at right now, and we have some initial results, is the sparse logistic regression. And it seems like the IHT is going to work in sparse logistic regression as well. Okay. So it was published last year. Thank you, everyone. I think I'm running out of time, so is that time? I think the questions.
There is one question. We can take one question. And Rachel, do you want to set up?
Something like this?
No. Yeah, 1 month. Yeah, exactly. Yeah.
Oh, sorry, the adversarial thing.
Exactly.
Right?
Yeah, I think it was
Yeah.
here. So, what kind of assumptions do you have? Do you have again Gaussianity on this?
Sorry.
What kind of assumptions do you need to get this bound?
Right. Again, so to get this, we need Gaussian measurements.
Exactly.
Yeah.
Yes, so that's what's expected. So how this inequality will change if you deviate from Gaussianity?
So we need something like this restricted
Sub-Gaussian tails. Yeah.
So sub-Gaussianness. Actually, it is super sensitive to being Gaussian. We have not been able, like even with sub-Gaussian distribution, these matrices do not have this property. The reason is that there is some quantization that is going on, right? So, and I said this rotational symmetry, even Bernoulli matrices would not have that rotational symmetry. Like you will not find an hyperplane that like at least in super small distances, right? So it's very sensitive. The analysis is very sensitive to being Gaussian.
Okay. Again, yeah. Thank you. So, have you looked at probabilistic bounds maybe for finite samples to get some, estimate of probability how different you are from the expected value
right.
for a
So,
finite sample?
Right. I think you will not be so even with non-universality, which we basically something works for. Even without that, you will not be able to improve on these things because there is this lower bounds, information theoretic lower bound that sort of holds. So yeah, so I'm hiding again. There is a tilde, so there are some log of 1 over epsilon and log of 1 over delta, 1 over tau terms over here. And maybe in that regime you will be able to do something.
Okay. Thank you.